Today we are talking about the racing machine, the 560, and this 560 was designed and produced by many people in the factory, but Kevin and me will talk today about the design, and because this is a Kevin's specialty, how to design foil.
Hi, my name is Kevin Elway. I work with AFS for the development and design of foils. My background in foil design comes mostly from the moth foiling class. I designed the Exocet and the Aeroset foiling moths, which have won 6 out of the 7 last World Championships.
Wing foil, racing foil needs to have good takeoff because you have small sails, you are probably sinking in the water with small boards, so you have to keep good takeoff abilities. And also, when you are above the water, when you are flying, you have to go upwind, downwind with good VMG, good speed, and to perform in each of kind of condition, low wind, strong wind. That was the first technical challenge of this foil. So all this data will make some design choices, and that's why we are working together, how to have the right foil will fit with the racing characteristics.
So Emmerich specified to me what he wanted the foil to do. So as he's just said, early takeoff, high VMG upwind, high VMG downwind, the ability of the foil to glide through holes in the wind, for the foil to be stable when overpowered with a big wing. You don't want it doing this. We were looking for a compromise between maximum top speed, early foiling, and good VMG. Okay, so when we're looking at a foil design, the first thing to consider is that there are 3 types of drag, and we're trying to minimize each of these. So there is induced drag, which is produced by the foil producing an upward lift. And induced drag is related to the span of the foil. We also have profile drag, which is the friction of the water flowing over the foil. We want to make that as small as possible. And very importantly, we have parasitic drag. So that's the drag of the water flowing over the fuselage and up around the foil mast, and where it's cutting through the water surface even, that creates additional drag. And we want to minimize these. So the first thing that we did was to improve the connection between the fuselage and the wing, such that the fuselage creates the minimum amount of interference with the wing. And we also made the fuselage as small as it could possibly be, so that it has the least wetted surface. The mast design is as slender and thin as it can be, subject to it still being stiff. And we also put these curves and blends in here. This is to help mechanically, but it also helps the water flow between the mast and the fuselage. We want the wing to take off early, so that would favour span. Also to have a foil that will glide through holes in the wind and glide through tacks. That favours span. But when we're looking at top speed, we actually get less profile drag if we have a wider chord. So there is a trade-off between the span and the chord, and so we need to get the right aspect ratio. This foil's got a span of 750, it's got an area of 560 square centimetres, which gives it a moderate aspect ratio of about 10. It's probably slightly higher than some other foils, but this is to give it good all-round performance. So the next thing we need to consider is the stability of the foil. And to create stability, the stabilizer pulls down and the wing lifts up. We need to create this torque in this direction. And we can do this by either having a short fuselage and a very big stabilizer with lots of angle on it, or a much longer fuselage with a much smaller stabilizer and less angle. Obviously, as we make the fuselage longer, we have more wetted surface on the fuselage, so more drag, but then we can have a smaller stabilizer. The other thing is that the stabilizer, because it's pulling down, that force has to be carried by the wing. So as we start to go very fast, around 30 knots, the load from the stabilizer adds a substantial load to the wing. So there's a trade-off between fuselage length, stabilizer size and the force. I spent some time trying to optimize this, and we came up with a fuselage which is 50 millimeters longer than the standard pure fuselage.
During racing, when you are going upwind, you have lots of counter heel, and sometimes happen that the tips of the front wing can breach the water surface, and what you want to avoid is to prevent ventilation on the front wing. You don't want to stall. So Kevin has worked a lot on this part of this foil to avoid all the tips ventilation.
The key to this is that, first of all, a section design is important. Some sections are much better at resisting ventilation than others. The shape of the foil from the front, you'll notice it's got a kind of bell shape. That's so that when this tip cuts through the water surface, it is more vertical than it would be if the tips rolled down like they do on some foils. And we also introduce twist into the foil, which means that the tips are operating at a lower load than the middle part of the foil when sailing upwind. And again, when we've tested it, the foil is very resistant to ventilation.
Yep.
It can sail with the tip substantially out of the water, very much like you'll see the America's Cup boats doing.
And also there is a double effect of reduce the tips angle, because you want to, when you design the front wing, you want to reduce all the torsion movement of this front wing, because torsion movement are also applying some torsion issue on the mast. So you want to put all the lift effort more in the center of the front wing? Yes.
The bending moment, so the amount of bending force that's transmitted to the middle of the wing reduces as the wing goes faster. And since the load on the front wing increases with speed, this means that we can make a smaller section here and a stiffer wing by this particular type of design.
We are using a quite thin section and with smaller chords, so it makes really a thin front wing. So it is also the same case for the stabilizer, and this part of the fuselage. We don't want to have torsion in the fuselage because you can have stability issue. So that's why this foil is made with UHM carbon fiber. And also the mast, when you try to reduce the thickness of the mast, you have to compensate the loss of inertia. That is why we are making our mast with high modulus carbon. Kevin have all his speed prediction. He can tell us what is the maximum speed potential, and we can check that on the water. So we always have to compare theory and experimentally data. So during this Weymouth Speed Week, we reached 30.5 knots for 500 meters. So that was close to prediction of this foil. But of course, during upwind and downwind race, it is not max speed that is important. It is more about VMG and angles during upwind or downwind. My perfect combo is quite strange, but it is more during a low wind condition, because the low wind abilities of this foil is incredible. So I really like to sail with this foil with the wild 7.2 square meters, because it is always incredible how early you can take off with really low wind. and how fast you can be with small foil and big sail in low condition. Personally, I really like to float on the water and be stable, because during tests you have to do lots of change on the beach with the gear, so I like to float. I'm using mostly the Fire 80 liters. It is a quite accessible foil because the characteristics we wanted for it make it quite easy for someone who have good foiling level and good wing foiling level, and for me it's quite an easy foil. Everybody can try this one, and after some tried will be familiar with this kind of foil. But of course, if you want to push this foil to 30 knots, it's gonna be a bit more work to do that. If we want to talk about the Pure 700, if you have the habits to sail with the Pure 700, it is a quite similar foil in terms of stability and low wind ability. It's quite similar. It is not an extreme foil. You can fly easily with really good speed. You can sail everywhere, go upwind, downwind. It is not a way like you will sail close to the beach and do a lot of tack. It is more about if you like to do sail and move a lot in your spot.
We can calculate things like the pitch stability of a foil, but there are dynamic things that happen when we're on the water. So because, say, this tip comes out of the water, it then applies a torsion load onto the fuselage, or perhaps a wave comes along and it hits the mast, that also applies a torsion load onto the mast. Anything that bends or twists or moves is destabilizing, and that would make the foil more difficult to sail, and therefore we wouldn't be able to keep the power of the wing going through the foil all the time. So it was really important to build this thing very, very stiff, and this is where the construction that Foil & Co have done with this monoblock construction all in one piece, and the ultra high modulus carbon fiber that's in it was absolutely key to the design.
Yeah, and another key in the design of this foil was the link between the foil and the board. So that's why we make this mast about 95 centimeters, because that was the right compromise between the thin profile and the UHM carbon, and that's why it make like super stiff, and you won't have any trouble about torsion or flex issue. So for more information or more data specification, you can go in the foilandco.com website.